Hi, theory of mechanism, velocity diagrams. Velocity analysis. In this session, we will study why velocity analysis is required, nomenclature associated with it, input required for velocity analysis, output desired from the velocity analysis, and formulas. When we analyze a mechanism or we want to design a mechanism, we are required to find velocities at various instants of time. There is a need to synchronize the production rate in case of automatic mechanism. There we require velocities at various instants of time. We also need to decide limiting values in case of metal to metal contact. There are certain limits beyond which linear velocity cannot be increased. Velocity analysis helps us in selection of bearings and joint articulation strategies. It is also used to find out momentum in a mechanism. Nomenclature. Let us understand the nomenclature of this mechanism. The figure shows a 4-bar mechanism that consists of a ternary link shown in green color and 3 binary links shown in red color, yellow color and blue color, with link lengths numbered as L1, L2, L3, L4. Link 2 is shown in red color. It is the driver link to which input is provided as a rotational motion omega. Omega is an angle turn in radians per second. Link 3 is connecting link and link 4 is driven link. Link 1 is fixed link and also called as frame. If L5 and L6 of link 3 are 0, then this ternary link becomes a binary link. Input required for velocity analysis is omega 2 and link lengths. Omega 2 is angular motion given to link number 2, which is shown in red color. After performing velocity analysis, we get desired output in terms of values of omega 3, omega 4 and linear velocities. What is omega 3? It is angular velocity of link 3. Omega 4 is angular velocity of driven link and Vb is linear velocity. Centers of rotation. Fixed centers of rotation and moving centers of rotation in the case of a 4-bar mechanism can be quickly identified as shown in this figure. To understand the virtual instantaneous center of rotation, we need knowledge of the direction vectors of 2 points. Perpendicular drawn to these vectors will intersect at a point called as instant center. Combined motion. A body can have simultaneous motion of rotation plus translation. End result from such motions will be that of combined motion. Instantaneous center of rotation. The points A and B of the link has moved to A1 and B1 respectively under the motion of rotation as assumed above. Therefore, the position of the center of rotation must lie on the intersection of the right bisectors of chords AA1 and BB1. Let these bisectors intersect at I as shown in figure, which is the instantaneous center of rotation, or also called as virtual center of rotation of link AB. The position of link AB changes with time. Hence, instantaneous center of rotation about which link is assumed to rotate will also change with time. Locus of this moving instantaneous center is called centroid. Instant centers of velocities. Now take an example of an automobile. Here is an example in which we are required to find the roll axis joining front roll center, which is virtual one, and rear roll center of rotation of a car body, again which is virtual instant center. Instant centers of velocities. Instant centers of velocities. This is a simple method to perform velocity analysis in planar systems. In this method, we draw lines, we find the intersections and ratios between every two bodies in plane motion. We can observe that there is a common point at which instantaneous velocity is same in each body. This common point is also called as instant center of velocity. Instant center of velocity can be actual common point between two bodies as shown in figure A, or it can be a virtual common point between two bodies as shown in figure B. Number of instant centers. For a mechanism containing n links, there are n into n minus 1 by 2 instant centers. For a 4-bar mechanism, there are 6 instant centers. Kennedy's rule helps us to locate virtual instant center between the links. The rule says that between every 3 links or bodies there are 3 into 3 minus 1 divided by 2, which is equal to 3 instant centers. These 3 instant centers lie on the same straight line as per the Kennedy's rule. Link 3 as shown in this figure has rotational motion around instant center I13. Location of instant centers. For a 4-bar mechanism as shown in this figure, there should be 6 instant centers as per Kennedy's rule. You can see 4 instant centers in this figure. All these are primary instant centers, out of which 2 are fixed, that is I12 and I14, and the other 2, that is I23 and I34, are permanent instant centers. Our task is now to locate other 2 secondary instant centers or virtual instant centers. The table shown will help us to name and locate the centers of rotation. Location of virtual instant centers. Extend link 2 and link 4 such that they will meet at an intersection point which will be the virtual instant center I13. Now extend link 1 and link 3 to meet at I24. This will be 6th instant center. Velocity analysis using instant centers. Problem: omega 2 is given, which is known, and we are required to find out omega 3 and omega 4. This is a classical example of 4-bar mechanism. Let us see how to find omega 3, that is angular velocity of link 3. Vb linear velocity of point B and omega 4 the angular velocity of link 4 quickly using instant center method. Va can be found from given data as per the formula. Va is equal to omega 2 into crank radius, that is O2A. Now extend O2A and O4B so that these lines will intersect each other at a point that we will call I13, virtual instant center. Now measure I13A and I13B. Solution: omega 3 will be VA divided by I13A, VB will be omega 3 into I13B, and omega 4 will be VB divided by O4B. You can try this sum using mechanism analyzer software. Slider crank mechanism. This animation shows movement of instantaneous center of connecting rod, that is link BD. In this figure you can notice 5 instantaneous centers. The sixth instantaneous center of rotation of the slider will be always at infinity if we can imagine slider travel as a very small part of a circle having an infinite radius. Illustrative example of slider crank mechanism. Draw this figure to suitable scale. The crank AB has a constant clockwise angular velocity of 2000 rpm. For the crank position indicated, determine the angular velocity of connecting rod BD and velocity of piston P. Solution: Step 1. Determine the velocity of B from the given crank rotation data. Omega AB will be equal to 2 pi n by 60, where n is rpm. It will give us the value 209.33 radians per second. So from this, Vb can be calculated as AB into omega AB from this formula omega r. Now put a value of AB in meters, 0.076 meter into omega value, that is 209.33. It will give us a value 15.9 meters per second. The direction of velocity vectors at B and D are known and shown in blue color and orange color in this figure. Solution: Step 2. The instantaneous center of rotation of connecting rod BD is at C, which is the intersection of the perpendiculars to the velocities through B and D. Now measure BC, which will be equal to 0.257 meter, and CD, which will be 0.214 meter. Solution: Step 3. Now we need to find out omega BD, that is angular velocity of connecting rod BD. Now we know the formula VB is equal to BC into omega BD. In this, VB is known, BC is known, omega BD is unknown. So omega BD will be equal to VB divided by BC. Upon calculation, we will get omega BD is equal to 61.88 radians per second. Solution: Step 4. Calculate the velocity of D based on its rotation about the instantaneous center of rotation. this will be the velocity of piston as well. So Vd will be equal to Cd into omega Bd. Upon putting the values, we will get velocity of piston, which is Vd equal to 13.25 meters per second. Let us solve this problem. Given crank AB rotates at a constant speed omega equal to 150 radians per second. You are required to find velocity of P piston when theta is equal to 30 degree. The procedure is same as that of illustrative example. Velocity analysis of a 4-bar mechanism using vector polygon method. Let us understand this method by solving a numerical. In a 4-bar chain shown, the crank AB rotates at a constant angular velocity of 10 radians per second in a clockwise direction. AB is equal to 0.2 meters, BC is equal to 0.4 meters, CD is equal to 0.3 meters, AD is equal to 0.55 meters, and angle DAB is 45 degree. For the given position, draw the velocity vector diagram and determine the velocity of point C and angular velocity of link BC. Draw space diagram from the data given in this numerical. Now we will see the procedure to draw velocity diagram. Velocity of B relative to A is perpendicular to AB and has a magnitude given by VBA is equal to omega BA into AB, that is equal to 2 meters per second. Now vector representing this velocity BA can be drawn to a suitable scale. In consideration of link AB, a velocity vector BA can be drawn as per the direction shown by vector VBA in the space diagram shown by dotted line. Now consider the link BC. We only know the direction of the velocity vector CB and the magnitude is unknown. Draw a line perpendicular to BC of space diagram from point B on the velocity diagram. Endpoint C is unknown at this moment. Now consider the link CD. Point D and point A both are fixed. That means their relative velocities are 0. Hence, point A and point D occupy the same point on velocity diagram. Now draw a line perpendicular to CD. It will intersect previously drawn perpendicular line from B. This intersection point is C. Now measure the lengths of vector CB and vector CD on velocity diagram to get the desired output. Now the calculations can be done as per this sheet. You can verify your answers as per this slide. Now let us see how to use velocity vector polygon method to solve slider crank problem. Numerical 2. A slider crank mechanism consists of a crank of length 250 mm which rotates at constant angular velocity of 20 radians per second and a connecting rod of length 900 mm. At the instant that the crank makes an angle of 30 degree from the IDC position, calculate the velocity of slider and velocity of midpoint of connecting rod. Step 1 of the solution is to draw space diagram with suitable scale and find VCD, that is linear velocity of point C on the crank CD. Thus VCD will be equal to angular velocity of CD into crank length CD. As per given data, it will be equal to 20 into 0.25, which is equal to 5 meters per second. Solution is shown in this figure. We had drawn vector CD which is perpendicular to crank CD in the direction of rotation of C with suitable scale. Then we don't know point B. Point B is slider. Point A, which represents the cylinder, is fixed, so it will coincide with point D on velocity diagram. So from point C we will draw a velocity vector perpendicular to CB with end unknown, and later on we will draw a velocity vector representing the linear motion of piston B or slider B, which will be of course parallel to the motion of B from point A. Now this vector will cross or intersect the line drawn from C at point B, and we will finally find out point G using similarity of the triangle principle. Numerical 3. A quick return mechanism shown in this figure consists of a crank CB which rotates clockwise at 500 revolutions per minute and is connected by a slider B to a lever AD pivoted at D. A further lever connects A to a slider E which is caused to move slowly to the right and quickly to the left. AD is equal to 0.5 meter, BC is equal to 0.1 meter, AE is equal to 0.35 meters. At the instant that the angle BCD is equal to 45 degree, calculate the velocity of slider E and angular velocity of AE.